We've seen that chemical reactions can continue to occur at the molecular level, even when nothing appears to be changing at the macroscopic level. That's because chemical reactions are reversible. The same sequence of events that can turn reactant molecules into product molecules can be reversed to change the product molecules back again. When reactants and products are in equilibrium, the reverse and forward rates are equal, and we can express the balance of reactants and products present at that condition using a mathematical expression for the reaction quotient Q, and its numerical value at equilibrium is the equilibrium constant K. That's Q for the quotient and K for the constant. That last one makes more sense if you speak German. At a given temperature, any chemical system has one unique numerical value of the equilibrium constant K. No matter where the system starts, no matter what the initial value of Q, it will always turn into K. Too much of this, too little of that, well, the forward and reverse reaction rates won't be equal, and that condition will shift until K is achieved. If you have a system at equilibrium and perturb it in some way, again, Q won't be equal to K anymore, and the reaction rates will adjust until we return to the equilibrium condition. How does the reaction shift back to the equilibrium state, and how can we tell which direction that will be? Can we control these changes and these shifts in order to maximize a reaction yield? We can use a very simple qualitative guideline to predict how an equilibrium system will respond to any perturbation. Now, it's best to analyze these changes quantitatively and to explain them in terms of the underlying reaction rates. But the initial qualitative idea is called Le Chatelier's principle. Le Chatelier's principle can be summarized like this. If a system at equilibrium experiences a change in concentration, pressure, or temperature, the system responds to partially offset that change such that the equilibrium will be restored. We need to look in turn at how each of these three things can affect a system at equilibrium. For each one, first we'll use Le Chatelier's principle to qualitatively predict that result. Then we'll analyze reaction quotient Q to quantitatively confirm that prediction. And finally, we can use reaction rates to explain the result. In each case, the key idea to Le Chatelier's principle is this. If you disturb an equilibrium, the system will respond in an attempt to undo the change that you've just applied. The new equilibrium won't look exactly like the one you started with because you did make a change, but the system attempts to undo as much of that change as possible. The reason for this has to do with the reaction quotient Q. At equilibrium, Q equals K. If you make a change to the concentrations, or the total pressure, or the temperature, Q doesn't equal K anymore. So the system responds and shifts until Q and K are equal again.
A timely reminder.
Usually, concentration refers to the molarity of a solute dissolved in solution. But reactions can also involve gases, and they also have a concentration. Recall that for gases, PV equals nRT. We can rearrange that. P equals N over V times RT. N over V is moles over volume. In other words, that's the concentration. This form of the equation tells you that concentration is directly proportional to the partial pressure of a gas. So, at a given volume, changing the pressure of an individual gas is exactly the same thing as changing its concentration. So for the purposes of Le Chatelier's principle, when we say concentration, what we really mean is concentration of a solute or partial pressure of a gas. Both of those things appear in the reaction quotient Q, so if we change either one of them, we will affect the equilibrium. The first case on our list of things that can affect an equilibrium is a change in the concentration of a material. If we increase the concentration of a reactant or decrease the concentration of a product, Le Chatelier's principle says that the reaction will shift away from the added reactant to remove it or toward the lost product to restore it. Overall, the reaction shifts toward products, turning reactant molecules into product molecules until the equilibrium is restored. And the reverse is true. If we decrease the concentration of a reactant or increase the concentration of a product, the reaction shifts in order to turn products back into reactants. Again, the equilibrium is restored. Quantitatively, we can look at what these same concentration changes will do to the Q value. Q is a quotient, which includes concentration of product solutes or pressure of product gases in the numerator, and those of the reactants in the denominator. If we increase the concentration or pressure of a reactant or decrease that of a product, then Q becomes smaller. Q was equal to K, but now Q is less than K. The system has to shift toward products to turn reactants into products and make Q bigger again. And the reverse is also true. If we decrease the concentration or pressure of a reactant or increase that of a product, then Q is too big, it's larger than K. The system shifts back to reactants to turn products into reactant molecules and make the Q value smaller. Le Chatelier's principle can qualitatively predict the shift, and analysis of the Q values can quantitatively confirm it, but why is this actually happening? That has to do with the balance of the forward and reverse reaction rates. If we increase the concentration or the pressure of a reactant, there will be more collisions among the reactant molecules, and the forward rate increases. If we decrease those of a product, there will be fewer collisions among the products, so the reverse rate drops. In either case, the rates are no longer equal, and the forward rate is larger than the reverse. Overall, the reaction shifts right, and more reactants turn into products. And again, the reverse is true. Decreasing reactant concentration means fewer reactant collisions. Increasing a product leads to more product collisions. The reverse rate will exceed the forward rate, and the system shifts backwards. You can see that all three analyses agree. Le Chatelier's principle qualitatively predicts the direction of the shift. A comparison of Q and K quantitatively predicts the same result, and it can be explained in terms of the reaction rates. Le Chatelier will always tell you about the direction of the shift, but you should be able to explain the underlying reason in terms of the competing forward and reverse reaction rates. Let's see if you can apply Le Chatelier's principle to predict the effect on a system undergoing a concentration change. A flask initially contains an equilibrium mixture of 3.12 atmospheres dinitrogen tetroxide and 6.77 atmospheres nitrogen dioxide. They undergo the equilibrium reaction shown. Additional nitrogen dioxide is added, which increases its pressure to 8.30 atmospheres. When equilibrium is reestablished, the final pressure of dinitrogen tetroxide is less than 3.12 atmospheres, 3.12 atmospheres because the equilibrium is reestablished, more than 3.12 atmospheres. Now, think about how the system will respond to the addition of more product, which will increase that material's concentration. The system will reach a new equilibrium, but the concentrations and pressures of all of the materials involved will have to change in order to achieve it. That's right. Le Chatelier's principle predicts that an increase in the concentration or pressure of the products results in a shift back toward the reactants. Now, let's look in more detail at this example and see how we can predict and explain this result in a few different ways. Grab your pen. Le Chatelier's principle is a good qualitative tool. It tells us that the equilibrium will shift to partially offset whatever change we make. So, if we increase the pressure of the NO2 product, the system shifts in the reverse direction, removing the products and making more reactants. The N2O4 pressure increases. But we can also look at this more quantitatively, using Q and K. The system starts at equilibrium, so Q equals K, and we can calculate its value to be 14.7. If we add more NO2 and change its pressure, now there's a new value of Q, and it doesn't equal K. Q is too big. There are too many products, not enough reactants, so the system shifts to the left, removing products and making more reactants. But why does this happen? It's reaction rates. If we add more NO2, the collision frequency increases for the reverse rate, but it stays the same for the forward. The rates are no longer equal. Now the reverse rate is faster, so the system shifts to the left. The second example on our list of things that can affect an equilibrium is a change to the total pressure of the system. If we change the partial pressure of an individual gas by changing its amount, then that gas's concentration is changed, as we just described. But suppose instead we change the pressure of the total system, changing the pressures of all of the gases at the same time. Usually that's accomplished by changing the volume of the system. An equilibrium will still shift because those new partial pressures will lead to a new value of Q. Qualitatively, if we reduce the volume, we increase the pressure. And And Le Chatelier's principle says that the reaction will shift in order to offset that increase of pressure. The reaction shifts away from the side with the greater moles of gas particles because that change will drop the overall pressure of the system. If instead we expand the volume and decrease the total pressure, now the reaction shifts toward the greater moles of gas because that will help bring the total pressure back up again. Quantitatively, we can compare Q to K. What happens to Q depends on how the pressure changes at the molecular level. Let's get small. Suppose we have a gas phase system in equilibrium, like these three gases in this flask. We can use the pressures, which are proportional to the amounts of each material, to calculate the initial equilibrium constant. Now suppose we reduce the volume of the flask. If the volume decreases, all of the pressures of all of the gases increase. In this example, there are more gas molecules on the reactant side, in the denominator of the Q expression. If we double all the values, the value of Q decreases. At the higher pressure, Q is smaller. It's too small, smaller than K, because it too heavily favors the side with too much gas. As a result, the reaction must shift toward products, which increases the value of Q until it equals K again. Now there's more variability in this example. Whether Q becomes larger or smaller depends not only on whether the pressure goes up or down, but also on which side of the reaction has the greater number of moles of gas. Regardless of the outcome, this analysis will always agree with the qualitative Le Chatelier principle. Changing the total pressure of the system means that Q doesn't equal K, and the equilibrium will shift until it does. So why is this happening? Again, collision theory and the reaction rates can help us explain the shift. Suppose again that we reduce the volume of the entire flask to half its original value. That will double all of the pressures of all of the gases. We've doubled the concentrations, so there are more collisions of all of the particles in the flask. But in this specific example, those collisions will have a greater effect on the forward rate because there are more reactant gas particles to collide than product particles. The forward rate increases more than the reverse. So more reactants turn into products, the reaction shifts toward the right until the reaction rates are equal again. Once more, all three analyses agree. Le Chatelier's principle predicts the shift in a qualitative sense. Analysis and comparison of Q and K explain it to us quantitatively, and the reaction rates give us a rationale at the molecular level. Let's see if you can apply Le Chatelier's principle to predict the effect on a system undergoing a volume and pressure change. A 2-liter flask initially contains an equilibrium amount of N2O4 and NO2. They undergo the reaction shown. The flask is then expanded to 4 liters. When equilibrium is reestablished, we have fewer moles of dinitrogen tetroxide than there were initially, the same amount of dinitrogen tetroxide, more moles of dinitrogen tetroxide than there were initially. No. Think about how changing the volume of the flask affects the total pressure of the system and how the equilibrium will respond to that change. No. Think about how changing the volume of the flask affects the total pressure of the system and which way the equilibrium needs to shift in order to counteract that change. That's right. Expanding the volume decreases the total pressure. Le Chatelier's principle says that the system responds by shifting toward more gas particles so that the pressure will increase again. That means more NO2 and less N2O4. The last case on our list of things that can affect the equilibrium is a change in the temperature. The first two changes, concentration and pressure, both change the reaction quotient Q so that Q is no longer equal to K and the reaction has to shift in order to compensate. But temperature changes are different. A temperature change actually affects the reaction equilibrium constant, K. Changing concentrations drives Q away from K, so Q has to shift back. Changing temperature changes the value of K, so Q has to shift to keep up to it. How and why the equilibrium constant changes with temperature is a subject we'll look at in more detail later in the course. But we can still apply the qualitative reasoning of Le Chatelier's principle as long as we know the enthalpy change of the reaction. In an endothermic reaction with a positive delta H, heat is absorbed. It's as if heat is a reactant. So if we increase the temperature, we're adding heat. It's like we're adding a reactant, something that drives the reaction forward, so the system has to shift toward products. Decreasing the temperature removes heat, so the system shifts back toward reactants, which produces more heat to compensate. In an exothermic reaction with a negative delta H, heat is released instead. Now it's as if heat is a product. The reverse effects will be observed. Higher temperature drives the reaction back toward reactants to absorb that heat. Lower temperature pulls it forward in order to restore it. In this case, a quantitative comparison of Q with K is going to have to wait for a while. The change in temperature is actually changing the numerical value of K. We're going to look more closely at why and how that happens in a few weeks. Let's apply Le Chatelier's principle to predict the effect on a system undergoing a temperature change. A flask initially at 100 degrees Celsius contains an equilibrium mixture of N2O4 and NO2, which undergo the reaction shown. Delta H for this reaction is plus 57.2 kilojoules. The flask is then heated to 150 degrees Celsius. When the equilibrium is reestablished, there are fewer moles of NO2 than there were initially. There is the same amount of NO2. There are more moles of NO2 than there were initially. Now, think about the sign of delta H, what that tells you about whether heat is absorbed or released, and how the system will respond to an increase in temperature. If we've changed the temperature, we've changed the equilibrium constant. Q and K are no longer equal. There must be a shift and a change to the amounts of the reactants and products in order to compensate. That's right. A positive delta H means heat is absorbed. It's as if heat is a reactant. So increasing the temperature adds heat to the system, and it will respond by driving away from the reactants to form more products. Great. We can qualitatively predict changes to an equilibrium system using Le Chatelier's principle, and we can explain it in terms of reaction rates. But how do we know that any of this stuff actually works experimentally? To the lab! Here's an example of a reversible reaction that's easy to follow just with your eyes because it involves an equilibrium between two different highly colored cobalt compounds. Cobalt ions dissolved in water form this pink complex. But if I add chloride ions, it transforms into another material, which is blue. Chloride is a reactant, so the addition of chloride ions in the form of HCl shifts the equilibrium away from reactants toward the products, and the color will change. But I can drive the equilibrium back again by removing those same chloride ions. Silver nitrate will precipitate the chloride out of solution, and the chloride concentration will drop. That means that the equilibrium will shift back toward the reactants to replace those missing chloride ions, and will restore the pink color. Here I have a system for that equilibrium that's balanced between the two forms, about equal mixtures of pink and blue, so it appears violet. But I can drive this equilibrium with temperature. The reaction in the forward direction is endothermic. It absorbs heat as if heat were a reactant. So if I add heat, it shifts away from the reactants and forms the blue product. If I remove heat, it shifts back the other way, from products to reactants to release the heat in compensation, and it turns back to pink. So, today we explored a powerful concept called Le Chatelier's principle, which allows us to qualitatively predict how a system at equilibrium will respond to a change in concentration, in total pressure, or in temperature. We also saw how we can interpret that change in terms of a comparison of reaction quotient Q to equilibrium constant K, and how we can explain the result in terms of reaction rates. In your next class, you'll look in more detail at some systems that exhibit some behavior that may be a little unexpected. Then you'll apply the Le Chatelier principle in order to maximize the yield of an important industrial reaction called the Haber-Bosch process.